Hi there. I wanted to give you a chance to review very slowly the ideas of tuning that we've talked about so far in lecture so that you can review it at your own pace. And then if you have questions, you can post them to Piazza. And hopefully everybody's questions will be answered in time for the second midterm. So what we're reviewing is parameter tuning. As we've said, a parameter is any one of the kind of small knobs that we can tune on an algorithm of some kind in order to change its behavior. So for feature selection, for example, we have to tune, we have to set the number of features that we want to select, and that's a parameter that we could either just decide how we want to set it, and we've done that so far, or we could tune it. So we could use data to decide how best to set that parameter. Now, the simple way of doing tuning is the train test method. The hard version is cross-validation. I force you to learn the cross-validation approach because it will make you see whether you really understand cross-validation, first of all, but also because if you only have a small amount of data, that's the best choice. If you had enough data that you had the luxury of having a big enough training set and a big enough testing set by dividing your cross-validation set in half, you would just do that. It would simplify everything. But if you don't have that much data, then doing it the conservative way, which is slightly more complicated, is what you have to do. And so I teach it so that you will have that. Now, in the beginning of the semester, you divided your project data set into 3 segments. 20% was your development data, 70% the cross-validation set, which here you see divided into 2 squares, training data and testing data. And then the final 10% of your data set you set aside as a final test set, which you have not been looking at, and you will take out of the closet just the night before you turn in your final report. Now I'm going to lead you through the process of doing the tuning 2 different ways. I'm going to start with the simple train test method, and then we're going to move on to the cross-validation method. And we're going to use the example that we keep coming back to, that the parameter that we want to tune is the number of features to select. So before we can train a model over the training data, we have to decide how many features do we want to select. Once we make that decision, then we will select that number of features on the training data. Then we will use those features to train a model using that training data. Once we have the model, we apply it to the testing data to see how good it is. So we've built the model completely without looking at the testing data. So then we can believe the estimate of performance that we get when we apply it to the testing data. We didn't use the testing data to decide the number of features or which features or to build the model. So how do we do that? On the training data, we're going to divide it into 2 sets, a train set and a validation set. Then if we're trying to choose between 3 different values for how many features should we select, let's say 100, 1,000, and 2,000, we can, on the train data, build a model for each one of those values. And so, let's say we were doing it for 100, over the train set, we would extract the top 100 features. Then we'll train a model using that data on those 100 features. Then that model we will apply to the validation set, and we will get a performance value. We'll go through that process for each one of those numbers of features. So we'll have a model for 100 features, 1,000 features, and 2,000 features, and we can see which one gave us a better performance value on the validation set. So then we'll know which one is best, and let's say 1,000 came out best, then that will be what we're going to call our tuned feature number. Now, on the training data, we'll take that tuned feature number, and we'll extract that number of features from the training data. Now, we've already extracted that number of features over part of the training data, but we would get a different set of features if we extracted that number of features over the whole training data. So that's what we're going to do. Then we're going to build a model over the training data with those features. And that's the model that we're going to apply to the testing data. Now, if we do this in cross-validation, it's a little bit more of a complicated situation. So whereas we took our training data, divided it into training and validation to do the selection of number of features to select, in the last process I just led you through, if we were going to do it the cross-validation way, what we would do is do a cross-validation on the cross-validation data, that's the whole cross-validation data set, for each of those numbers of features. So that means for 100 features, we're going to do a cross-validation, which means that on every fold over the training data, we're going to select 100 features. We're going to train a model on the training data of that fold for that number of features that we selected, and then we're going to apply that model to the testing data for that fold. We'll do it for all folds, and we'll average. So we're going to go through that whole cross-validation separately for each number of features. And that will give us a performance value for each number of features, and we can see which one is best. And that will be then our decision of how many features should we select. Now, we have a performance value over this cross-validation set achieved through cross-validation. And a cross-validation, it's always the case that on every fold, what we train on and what we test on is different. So you might think you can believe the performance value that you got from that cross-validation. But since we're using this process to tune the model, to tune how many features we're going to select, then we actually use the whole cross-validation set to make the decision about how many features we should select. So if we had already decided how many features we were going to select, we could believe that cross-validation. But since we used the cross-validation to make that decision, now since that decision is part of what we came out with, then we have to have a different set of data that we evaluate that decision on. So that's why we don't believe that cross-validation result when we tune. So we need a more conservative estimate of how a model that we train on the cross-validation data using the decided upon number of features would do. So that's what stage 3 is for. So stage 1, we do cross-validation over the whole cross-validation set to decide how many features we should select. Then over the cross-validation data in stage 2, we select that number of features and we train a model over the cross-validation data. Then we use stage 3 to estimate how good that process we went through in stage 1 and 2 was for giving us a model. So to step through that, on every fold, we're going to take the training data and do what we did for the simple approach that we started with. We're going to take that training data, we're going to divide it into train and validation. We're going to build a model using each parameter setting on the train data and test it on the validation data. So we will have a performance value for each one of the possible values of the parameter. We'll see which one is best. Then we'll combine the train and validation set into a training set. Then using the decision that we made when we divided between train and validation, we'll train a model now over that whole training set. That's the square of data that's you see highlighted here with red dashed lines. Then we'll take, and that whole process we consider the inner loop. Now we're going to take the model we trained on the inner loop and apply it on the outer loop to the test set for that fold. Notice that we didn't use that purple data, the testing data for fold 1, at any point in deciding how to set the parameter or for building the model on that fold. And so the test set performance that we have from the outer loop we consider our conservative estimate of performance. And we're going to do that for every fold. And so then when we average across folds, then we have our conservative estimate. So we've got 3 stages. In stage 1, we decide how many features are we going to select. We do that through cross-validation. In stage 2, we build the model using the number that we decided was the number of features we should select. And then to estimate how good that model is, we can't directly measure how good that model is, but we're going to estimate how good that model is by measuring how good the process was that we used to build it. And so we're going to take stages 1 and 2, and we're going to do them on the training data for each fold. That's what stage 3 is. Now we may make a different choice on every fold for what number of features to select. And that's okay, because over different data, we would make a different choice. And there can be times when the choice that we make on the inner loop doesn't turn out to be what would have given us the best performance on the outer loop if we had perfect knowledge of the test set. That's okay too. That's what we want from a conservative way of estimating our performance. Now, when we did the quiz for week 11, we stepped through a tabular representation of this process. Here you see the table, and the bottom 5 rows represents the outer loop for a 5-fold cross-validation, and the top 5 rows represent the inner loop. The 4 columns A, B, C, and D represent settings for a parameter, and the numbers in the boxes represent kappa or performance values. So the way I would read this is, if I train over the segments of data that I see in the right-hand column in a row, and I test on the data that's in the, did I say right-hand column? I meant left-hand column. So here you see train as a left-hand column, then validation or test to the right of that, and then you see A, B, C, and D to the right of that. Okay, so let's say I'm in the first row. I will train on a segment of data that's made up of test sets Y2, Y3, Y4 put together. And let's say I do that for setting A, and then I apply that to Y1. I will get 0.68 as the performance value. Now if I train on Y2, Y3, Y4 using setting B, and I test on Y1, I'll get 0.5. So you can fill in this whole table that way. Say, so for in every row you have some data you're training on, some data you're testing on, and you've got the 4 different settings, and you've got the performance values. So stage 1 is a simple cross-validation. You can use the bottom 5 rows to simulate a simple cross-validation. The A column is the set of test set performances if you used setting A to build the model on every fold. And so you can consider that the baseline. So this part that's circled that you see, that's the test set performance across each of the 5 folds. And so if you average those, that's your average baseline performance. And you can compute a confidence interval around that if you want. Now, you can see here exactly how I computed the cross-validation result for each of the 4 settings. And you can see that C performs best. It gets 0.63, which is bigger than all of the other ones. And so stage 1 tells me I should pick setting C. And in stage 2, I'm going to build my model using setting C. But I don't know how good that model is. So let's see how good it is using stage 3. So for every fold, we're going to start with fold 1. We have to first do the inner loop to decide what setting that we want to use. So I'm going to go to the top portion of this table to find a row that I can use for the inner loop. So on fold 1, where my training data is Y2, Y3, Y4, Y5, I need to find a row that uses only those segments and doesn't use Y1. So the second row is the one that I'm going to use. Now you can see 0.6, 0.66, 0.58, 0.68. Those are the respective performance values for each setting if I train on the train set and test on Y2. And 0.68 is the one that's bigger. So my inner loop tells me to pick D. So then I'm going to pick D on my outer loop. And so my test set performance on the outer loop for fold 1 will be 0.56. I'm going to go through this process for each fold. So for example, for fold 2, I need to find an inner loop row that doesn't use Y2, and that's going to be the 4th row. In the 4th row, setting C is the best performing setting. So that means that for the Y2, for fold 2, I'm going to pick C. And so you can see I've circled C in the fold 2 row, and the performance value is 0.68. So I can compute then my stage 3 performance value for each fold. And the average is 0.63, which is just a little bit bigger than 0.62, which was baseline. On folds 1 and 5, you can see that this inner loop led me to make a decision that wasn't the best that I could have done if I had perfect knowledge of the test set. But I don't have perfect knowledge of the test set when I'm going through this procedure. So the only reason why I'm pointing this out to you is so that you can see that that's the case. And that's exactly what's supposed to happen. That's exactly why this is considered a conservative estimate. Now for assignment 8, we went through the same tuning procedure that you just saw me go through on that paper representation. And we used the experimenter mostly to set up the table, and then we used the explorer to do the outer loop. So we loaded, so for assignment 8, you had a whole data set, the RFA full.arff, and it was divided into train test pairs. So you set up the experimenter with the full data set and the training sets for each fold, as you see here. And then on the right-hand side, you put in 3 different versions of SMO, each one with a different exponent. Because what we were tuning here was the exponent. You can see here the experimenter fully set up. Then we're going to run the experiment, and then we're going to go to the Analyze panel so that we can see the result. And here it is. So you can see the first row that we get is, you can see the cross-validation result for the whole set. That would be for stage 1. And you can see that in stage 1, the best performing value was the 3rd version of the exponent, which was exponent 3. You can see that if you look down below. And then underneath that, you have the inner loop performance for each setting on each fold. So you've got 5 of these training sets, 1 for each fold, and those are the rows that are underneath that top row. So what you did then was fill in a table that was kind of like the table that we had on the quiz. So for each fold first, you fill in the test set, not the test set performances, but the inner loop performances, and these are built by the experimenter using cross-validation over the training data, not by dividing the training data into train and validation. But you could do it either way. Either way is valid. And actually this way that the experimenter does it is even better of an estimate of which one is best. So we've got what amounts to the top part of the table in the first 3 columns. Then next to that we have which setting would you pick based on the inner loop, and you can see on every fold we picked setting 3. To get the outer loop performance value, what we have to do is go to the Explorer. And for every fold on the Preprocess tab, we will load the training set. Then on the Classify tab, we will insert the setting that was best for that fold. So on fold 1, the best setting was 3. So we're going to set the exponent to 3. And we're going to load the test set for fold 1 as a supplied test set. Run the experiment to get the performance value, and then fill that in. And we can do that for each fold. Now, if we went through that same process, so for every fold, loading the training data on the Preprocess tab, and then going to the Classified tab, if instead of the optimal setting for that fold, we use the default setting, then we would get the test set performance for the default setting. So just as we have here in this table the test set performance for the optimized model, we can get the test set performance for the baseline model, and then we can do a significance test to see if there's a significant difference between the tuned performance that we're filling in the table and the baseline performance. So again, to see the significance test, you could compute your confidence interval by hand the same way you did on assignment 4, or you can do a t-test in Excel. Now I'm going to go through the short version, this sort of simple version of doing the tuning. We'll go through this in lecture as well, but I want you to be able to refer back to this. Now, you are not allowed to use CV parameter tuning for assignment 8 or assignment 9 or the practical part of midterm 2, but you are welcome to do this on your project. So we've already gone through the 3 stages of tuning, and we're going to do that here in CV parameter tuning or CV parameter selection as well. So first we're going to pick the CV parameter selection meta classifier from the meta folder. And when you look at the object editor, you'll see you get to decide which algorithm is it that provides the parameter that you want to tune. And then you have to tell it which parameter you actually want to tune. You can actually tune more than one parameter. So you see where it says CV parameters and then 0 java.lang.string. If you click on 0 java.lang.string, it brings up the object editor that you see with C.1, .8, and 8. So that's a little bit cryptic, but it just expects you to know that that's what you're supposed to type. So what have I entered here? The C is the parameter we're going to tune. That's the confidence factor. And now I have to tell it what's the lowest value in the range I'm going to test. And I'm setting here 0.1. And I'm saying the upper value that I want to test is 0.8. And I want to do 8 versions along this spectrum. So it's going to do 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. So I'll have 8 columns instead of 4 or 3. So I fill this in. That's the name of the parameter, the lower bound on the range, the upper bound on the range, and the number of values that I want to try out. Once I type that, I click Add. I'm going to do that for every parameter I want to tune. And then it's going to do all combinations, and each combination will be essentially a column in the table. Now, how did I know that I should have C? Well, if you look just above and a little bit to the left, you'll see J48. That's the name of the decision tree classifier. And you'll see some command line options. We've more or less ignored those. But if you look at the corresponding string for any algorithm that you might use, it shows you the command line call based on the values in the object editor at the moment. Now, the command line parameter names are always the first letter of the name of the parameter. So if I look in the J48 object editor, the only one of those slots that's tunable is confidence factor that starts with a C. And so I know that -C is that. There's also -M, and the only slot that's tunable is min number of objects. So -M must be minimum number of objects. So that's essentially how you do this. It's not very user-friendly. You could also look at the Java docs for Weka. It's open source and it's all in Java. So if you're a Java programmer, you could look at those and get the documentation. This is, really what I'm telling you is the only way that you can find it out. I know that doesn't sound very nice, but that's what Weka has given us. Okay. I want to say, you'll see here also num folds. So you get to decide how many folds you want for stage 3, and that's what num folds is. Okay, so now, if I set up CV parameter selection the way you see, and I've configured it the way we just stepped through. So I picked J48 as my algorithm. I said I want to tune parameter C. I want to look at 8 different values for the confidence factor, 0.1, 0.2, etc., etc. I want a 10-fold cross-validation. Now, when I click Start, it's going to run all 3 stages of tuning that we've talked about. The first thing it's going to do is tell you what was the result of stage 1. It says classifier options -C 0.5 -M2. So it tuned these parameters, and these were the values that it picked out as best in stage 1. Then if you scroll down, you see the model. That's the model that it built in stage 2. And then if you scroll all the way down to the performance value, what it tells you, all this performance information, that's from stage 3. Now it doesn't label the stages because those are labels that I gave those parts of the stages. But you should know what happened that produced that output, and that's why I have required you to go through and learn how to do this tuning so that when you see the output that Weka gives you, you'll know where that came from. Okay, now I think you're fully prepared. So go through this video as many times as you need, and good luck.